The last lesson of this chapter regards a class of equations of functions that require another unknown to be defined. This other unknown is called the parameter. I use here an example that I borrowed from physics. This has to do with the projectiles. All right, you don't need to know that. It's just an equation that is dear to me, and that's why I use it. So let's look at this example. Just for context, this represents something that is being thrown like this, all right, in which this is the speed with which, or the velocity with which is being thrown in that direction. And this is the trajectory of the object falling, all right? And this S over here is the vector that determines its position as it falls, all right? So this is the Y direction, this is the X direction, and obviously the position of the object is going to depend on a quantity that is not represented over here, which is the time, all right? And this is what you have over here. The horizontal projection of S is going to be defined like this, 10t, all right? This 10 is the original speed, by the way. And the vertical projection of S, the vertical component, is going to be defined by this equation, in which t is the time. So if you plug in different values of t over here, so 0.1 second, 0.2 seconds, 0.3 seconds, the positions of x and y are going to be different. But t is not represented here on the graph. So it is the parameter. So how do you differentiate this? In order for you to differentiate this, I'm going back over here at the end, but right now I'm focusing on how to differentiate the expression. All you have to do is to follow the rules again. dy by dx is what? We can use again the product rule to differentiate dy in terms of the parameter p, all right? And if we do that, we just need to put times dp by dx. But dp by dx is what? Is 1 over dx by dp, right? So you can rewrite this just as this. dy by dx is dy by dp divided by dx by dp. So differentiating parametric equations is actually very simple. Just differentiate each one in terms of the parameter and divide the derivative of the expression in y by the derivative of the expression in p, the derivative of the expression in x in terms of p, and the expression is going to be what you want. Just one note over here, because you can always get an expression of y in terms of x if you eliminate the parameter t. So in this case, that's what I did. I eliminated t by putting t equals x over 10. I substituted on the bottom equation, and eventually I get this, all right? This is called, in this particular case, the equation of the trajectory. And you can always differentiate this in the traditional manner. But it will be actually simpler if you just use this method, all right? Let's see. What is dy by dx? Dy by dt is what? If you differentiate this, it's just going to be minus 10t, right? If you differentiate the x in terms of t, that's just 10. So dy by dx is this divided by that, so it's just minus t. All right? You have here an expression for the dy dx in terms of the parameter. You could always differentiate this to have an expression for dy dx in terms of x, all right? But our purpose right now is to get an expression for the derivative in terms of the parameter, and that's just what we did. So what is this minus t? This is the gradient of the trajectory in terms of the time. Is the gradient of the trajectory in terms of the time. just plug in the value of the time and you automatically know the gradient of the trajectory. All right? Just a parenthesis here to make sure that you understand that this is just an example. What I'm just saying about trajectories and projectiles, etc., is valid for any other situation that you will have with whichever parameter, okay? So, if we want to find, again using this example, the equation of all tangents in terms of t, what do we need? We already know an expression for all gradients in terms of t. So we just need the y-intercept. So we already know that this m is minus t. So all we need is a point that we know that belongs to the line. And we can use this generic point over here. The 10t and the 20 minus 5t squared. So if I substitute on the equation of the straight line these values, that's what I did over here. And so for c, I get that c equals 20 plus 5t squared. Substituted back on the equation, and here you have the equation for all the tangents in terms of t. I can use the other method, which is just subtracting the coefficients of the generic point in y and x, and you automatically get the equation. So, as an example, what is going to be the equation of the tangent when the time equals 2 seconds? Go over here, substitute time by t by 2, and you have here the equation of the tangent on time t equals 2 seconds.